Then sharing the screen now. Okay, so today the plan is to go over the general equilibrium chapter and then do some class exercise at the end. So right now, remember, you have to go over the videos of consumer theory and the partial equilibrium, competitive equilibrium analysis. So right now we're going to go to general equilibrium theory, and the main difference with the previous chapter is that here we're not going to have this nice separability coming from quasi-linear utilities. So there's going to be more complications in terms of the theory we developed. So it's no longer true that just first order conditions can characterize this. We're going to, of course, do a smooth transition. So the first is going to be very similar. And then as we go through, we're going to understand the main differences. In particular, the previous chapter had a striking property. It was that the distribution of endowment didn't matter for the final allocation of the non-numeraire good, okay? So that means that, for instance, if I change the income in everyone in the economy, so the market of cereals, which is a market that doesn't depend much on income, right? So what cereal do you buy in some societies, you know, will be a small part of the total expenditure. So that means that so changing the income distribution around won't mess with the allocations in the market of cereal. So that's important because then you can study that market in an isolated way. And that basically comes to the fact that this is a separable market, right? And quasi-linearity does the magic that allocations in the cereals market will be isolated, right, from the rest of the market. And in particular, the distribution of income doesn't matter. So when the distribution of income matters, then things get way more complicated. Okay, but now we're going to study a toy version of the complicated model. And this is the famous Edgeworth box. Okay, so today we're going to understand that. So the first economy we're going to study is a very simple economy called pure exchange economy. And this is the famous Edgeworth box, which basically has two consumers. So there are consumers indexed by I, indexed by 1 and 2, and then two commodities, 1 and 2 as well. Now you have consumers I, consumption vector, is basically an array that is indexed by I. This is the Einstein notation. So when we remove one of the indexes, in this case L, it means that is the vector in the other index. So here, for instance, we have a consumption of good 1 and good 2 of consumer I. And then, of course, we have this matrix of allocations, which is indexed by two indexes, L of goods and I of individuals. Okay, so the consumption set of each individual right now can be different. So it's subindexed by I. But right now, for simplicity, we can fix it to the same for both. And this is just the R plus in 2 dimensions. Okay, so we have also preferences. Preferences can be different in principle, and they are defined over the possibly different consumption set. Each consumer has an endowment. So remember, what was endowment? So an endowment is the physical quantities that there is in an economy of different goods. So I want you to imagine pretty much an experiment where I pretty much bring two of you, right, two students to a laboratory. And then I give you an initial allocation of, so I have an experimenter. I create the total endowments in the economy of being total to 10 apples and 10 oranges, okay? So that's total endowments. So 10 apples, 10 oranges, two goods. Then I give, I'm going to give 3 apples, right, to the student 1 and 7 apples to student 2. And then the opposite for oranges, right? So 7 oranges for student 1 and 3 oranges to student 2. Okay. This initial allocation is the endowment. So when I said what are the oranges that I give to student 1, so I is equal to 1, and oranges, L is equal to oranges, this quantity will tell me how much initial quantity of goods, physical goods, I will give to these agents. This initial endowment can be 0. Okay. In particular, in this particular exchange economy, there is not going to be production. Okay. Only the free disposal technology. So nothing is produced, only exchange happens. Okay. So you're pretty much are stuck with endowments, and then you have to trade. Okay. So consumer's endowment vector is given by omega I, and is this vector of, again, same as consumption, omega 1, good one, apples, and omega 2, oranges to individual one. The total endowment in the economy of any good is Einstein notation again, omega L, now without the I item there. So now this is the summation of omega Li plus omega L2. So this is for good one, you fix the good, and you add up the total quantity in the economy. So in this laboratory where I brought these two students, how many total apples and oranges there are? 10 of each, 10 apples, 10 oranges, okay? So this is omega L, is 10, okay? Okay, and then this is important. We're going to assume that there are positive quantities of all in the aggregate. So it might be that because of the experimenter, some agent doesn't get anything of oranges, right? Or no apples, but in the economy, the total quantity of apples and oranges will be always positive. So here, because there is no production, it makes no sense to have zero quantities of any good, because if there is no physical good, there is no trade. So this is a situation is not interesting for this theory. Okay, so aggregate quantity of endowments is strictly positive. Everyone understands that? So far the notation is X consumption bundle, so this is actual consumption. Omega is the endowments of physical quantities you are given at the very beginning of the experiment. Now, what is a feasible allocation? So feasible allocation is consumption of good L by individual 1 and individual 2, and this consumption has to be less than or equal than omega. Why less? So in some cases, consumers may not want to consume the total 10 apples, right? So they may leave something and throw it to the trash. So in that case, when there is no monotonicity or no local association, then you can actually dispose of this excess demand. So you can throw it to the trash. Formally, mathematically, this means there is a production set. Okay, so even if there is no physical production of new goods, you can still dispose of existing undesirable goods. So a garbage can in this laboratory setup is also a production set, okay? And so mathematically, this set is equal to the negative quadrant of R2. So basically, you can throw away freely anything, okay? There is no cost to throw it away.
Victor, Victor, I have a question.
Yep.
For here, don't we need utility functions like to show like they hold with equality or?
Well, we define preferences, right, at this stage, so they're more general. So in particular, versus you can have a pure exchange with lexicographic preferences, and there is no utility, right? So right now, each of them is endowed with a preference relation. And now, so for your core exam and for and the rest, actually, you're gonna I'm gonna warn you, right? So if there is a source of questions that is so pretty much overrepresented in the core exams, is the Edgeworth Box. Okay. So why? Because it's so simple and tricky that basically this will be able to test you on all concepts on general equilibrium. So for sure you're gonna see some Edgeworth Box. Okay. So pay a lot of attention. But and also the second point going to Schumann's question is that part of the questions that people do. So remember, the core exam is not only done by me, but also by 3 professors, right? So whoever is going to teach you the second year, next semester, sorry, and then a third professor, which is usually someone neutral. I think last year was Maria and Bruno. So this year, who is teaching you next semester?
Bruno.
Yeah, so it's going to be the same, I guess. So Maria and Bruno. So Maria, for instance, asked a lot of questions about the Edgeworth Box, right? Sometimes I ask about the Edgeworth Box, sometimes I don't. I focus more on decision theory. And then Bruno, he usually focuses on game theory. But Edgeworth Box usually appears a lot for this third person, right? Because this is a classical question, general equilibrium. So part of the tricky questions that people like to ask here, remember I'm preparing you for the exam also, right? Is that you give some weird preference relation, like a lexicographic preference. So do the Edgeworth Box with lexicographic preferences. So what I mean by that is that at this particular stage, the way you should approach this is by trying to understand, the whole concept in a very, very general way, such that you're able to adapt to any tricky question. So here, learning just the shortcuts and the more standard models won't work, because the nature of these questions is usually trick questions. So I don't like those kinds of questions, but that's how it works, right? And this is in most places. Yeah, but I'm going to explain more as we go. But yeah, so right now we're super general. So preferences, they may not even have a utility representation, right? For instance, lexicographic preferences. Or for instance, you can change the rational model with another model, right? That are basically non-complete and transitive, and you can still define a general equilibrium, right? So, but most of the models that you're going to see in the core exam are rational models, okay? Now, if they are not from me. Now, so what is the key of this Edgeworth box? So the key new feature in the model we're introducing is that income before was exogenous, right? While now is endogenous. What does it mean? This equation here. So each agent basically can buy other goods. And how can you buy other goods? Basically, you have an income, right? And what is that income? Well, it's just price multiply inner product with endowment. So what it means in the laboratory setup is these guys, so two students, come up with some exchange rate. So how many apples will I exchange for an orange? Okay. If both agree, this is a price. Okay. So an exchange rate between apple and oranges is a relative price, P1 over P2. These models, because of homogeneity of degree zero and other properties that we have here, they are going to be completely determined by the relative prices. So what basically you're doing is you normalize one of the prices, apple and oranges, to 1, and then that means I can define the relative price in terms of this exchange rate of how many units of apples I'm willing to exchange to units of orange. This is a price that is going to be able to create an equilibrium. So a price may not be an equilibrium, right? So we are going to talk in a second about prices that are equilibrium only. But initial exchange rate, right, it has to be basically commonly agreed by the two agents, right? We're going to explain more about prices, but again, this is not a theory about price formation. It's only, it's a mathematical construct that is going to be a nonlinear system of equations, okay? So the income is given by the multiplication of prices, which is this number that both agree and see, multiplied by the endowment of the good one of individual I, and multiplied by price of 2 of endowment of good 2 of individual I. So the cool thing and the new thing here is that the budget constraint now doesn't depend on income. Income is no longer here a parameter, okay? Parameters are things that are given to you, exogenously given. Okay, so now income is endogenized. Okay, so in this model, income is endogenized. Now the consumer can buy things that are less than equal the prices multiplied by the endowment. So of course, my consumption has a price, and therefore the total expenditure has to be less than equal than my total endowment multiplied by prices, which is the new income. Everyone understands? So this budget looks a little bit symbolically like the chapter 3 Mascodel, Winston and Green budget, but it's not the same. Okay, I want to be clear. This is endowment is a vector, right? And so, and in fact, this, if you were fixing the endowment, so also a big caveat here, Mascodel has bad notation. So omega is an endowment, right? This is the experimenter that is fixing these initial quantities of goods, apple and oranges. Mascodel omits omega from everything, right? But omega is in fact a parameter here, okay? So this budget thing, fixing omega, so right now, that's why we're not writing it, of individual I is basically this inequality given this vector, okay? So everyone understands now income is endogenous. The new parameter is endowment, okay? So now for each price, I get a different endowment. So what happens here? So imagine these two agents say, now we agree that 2 apples are worth...
Sorry for the interruption. So when you say income here, it's the P times omega?
Yeah, so it's a way to call it. I mean,
Okay.
mathematically it's P times omega, right? But that's the new budget you have. So that's the amount you can spend at most. So the idea is imagine I come to this experimental setup. I give these three apples to the agent 1, 10 apples to agent 2, 7 oranges to individual 1, and 3 oranges to individual 2. Who is richer in this setup? Well, you don't know. First, if you fix a price, now you know, right? For some reason, these agents, agree that a good exchange rate is 2 apples, 1 orange, right? Because commonly, they like more, obviously, the oranges, okay? 2 apples, 1 orange. So if that happens, then the guy that has more oranges is richer, right? So what I'm saying is this is completely endogenous with the price formation, right? So if in another economy, different guys that comes to the experimental setup decide that exchange rate is instead 2 oranges, 1 apple. Now, who is the rich guy? The guy that has more oranges, right? So here in the income, wealth, how rich you are, depends completely on the prices, okay?
So and prices are endogenous as well, right?
The prices are going to be endogenized in a second. Right now, this is all a function of prices, okay? So you can imagine here an auctioneer, so screaming prices and saying, okay, this is the new price. And then, immediately you know how rich you are, okay? But these prices, don't force you to trade because people may not agree. So right now, you have the auctioneer screaming prices, and these agents just compute how rich they are. And then we're going to go to the second step, which is trade, okay? So again, let's define a notion of equilibrium that is going to endogenize prices. So a Walrasian equilibrium for an Edgeworth box economy is a price vector, okay, and an allocation X star. Allocation is all consumption of 2 goods of individual 1 and individual 2, okay, such that every agent maximize their own preferences given their own endogenous budget, okay, for the price of equilibrium. So this means that the auctioneer keeps screaming exchange rates, right? So it says in this laboratory setup, the auctioneer, which is the experimenter, says 2 apples are worth 1 orange, right? And then one of the agents say, I don't want to to give away my endowment. So even if it's feasible to change it, I don't want to try, right? And you keep going. And then eventually, right, when both agents feel they maximize their preferences, right, subject to their endogenous income, then given the price the auctioneer just shouts, then you're done, right? So both guys are happy, and then this becomes an equilibrium, right? So at this stage, they create a mutual beneficial exchange where both benefit from this exchange at these prices, and this becomes an equilibrium, okay? So remember, an equilibrium also here, this definition allows you each of these agents to remain with their initial endowment, okay? This equilibrium also allows you to throw away things. So for instance, if you don't like oranges, so nobody likes oranges in this economy. Imagine preferences that are such that both hate oranges, right? So this also can allow you to basically throw away all oranges, right? At no cost. Okay, so we're going to understand this in a second. So of course, these are the complex versions of this model. Now let's understand the most clean, nice version of the Edgeworth box, which of course comes from the form of a Cobb-Douglas. So imagine—
Sorry, I have a question. At this stage, based on the intuition, I don't know if we can assume a trade will happen if one consumer has the endowment dominant the others. I mean, one consumer has more apples and more oranges. So
yeah. That's a good observation. However, so remember, here we're defining an equilibrium situation, right? Just requires that everyone maximizes their preferences. So the question that who asked this was Fenghua.
yeah.
Okay, so basically this question is related to 2 properties of this model. The first one is existence, right? So is there, in fact, any price at which everyone maximizes? Maybe not. So we haven't established existence. And in fact, existence is not guaranteed unless we assume more stuff. So preferences right now are too general to ensure existence, okay? So when we add properties to our preferences, then we can ensure existence, okay? So the answer is yeah. So at this stage, we have no guarantee that there is existence. So is there any price at which there is a trade? And in fact, there is this mutual beneficial exchange in the well-rational equilibrium, okay?
And uniqueness as well, Victor. We do not know.
Uniqueness even worse, right? So we even assume that we assume enough to have existence. Uniqueness may not happen, okay? So the key property of these models is that these models are completely crazy, right? So you can generate infinite equilibriums, you can generate non-existence. So yeah, so that's why it's a goldmine for trick questions, okay? So be warned that, yeah, so uniqueness and existence, usually if you don't have existence, so a typical question could be, show that there is no equilibrium, right? So that's fine, and then you're done. But most complex questions are, there are many equilibriums. So equilibria characterize all of them, right? So yeah, we're going to learn some stuff about that. But these models are very tricky. Now, we're going to discuss more the epistemology more than the exam, because this is kind of problematic if you're thinking of a scientific model. So we're going to discuss that in a second. But before that, let's go with the simple stuff, right? So let's understand a simple toy model with Cobb-Douglas so we visualize what's going on. So Cobb-Douglas example. So suppose you have two consumers and each of them have the same Cobb-Douglas, okay? So the Cobb-Douglas here is consumption of individual I of good one to the alpha. Alpha is common, so not same preferences, right? However, the actual value of the utility may differ. Why? Because they may be consuming different quantities, right? So it's the same utility function, but not the same experience utility, right? It depends on the consumptions. Now, what are the endowments? So you have two apples, two oranges. Individual one has how much? Has basically one apple, two oranges. Individual two has two apples, one orange. Okay. And then we're looking for a price that pretty much creates this mutual beneficial trade. So let's compute the wealth according to these prices of individual one. So what is the endowment of individual one? One apple, two oranges. So what is the price of one apple? P1. What is the price of oranges? P2. What is the income of individual one? P1 plus 2P2. Okay. Now, what is the income of individual two? Is 2P1, right? Plus 1P2. Got it? Now, I'm going to introduce this object, which is very cool, which is called the offer curve. So the offer curve is the Marshallian demand that we learned in chapter 3, okay? That before was a function of prices and income, right? But now, because income is endogenous, it's just a function of prices. And of course, of endowment that is always hidden, right? But here, endowment is a number, a vector. So now, what is the offer curve of individual one according to the price P? So at this point, you should know the Cobb-Douglas by heart. So it's alpha of the income, right, divided by the own price, P1. And then what is the consumption according to Cobb-Douglas of good 2? 1 minus alpha of the income divided by P2, right? Now, because here income is endogenous, I replace it by the endogenous income, right? So P1 plus 2P2, okay? P1 plus 2P2. So now this becomes a function of prices, right? So if you plot it basically for different prices, this is telling you how much the consumer is willing to exchange. That's why it's the offer curve, right? So of course, plotting it is not easy because you have two parameters, P1 and P2, right? So it's a 3D thing, right? So basically you have the Y and X axis are P1 and P2, and the Z axis is the offer curve, right? So it's no, actually it's 4D, so I cannot even plot it, okay? Because it's two goods here. So yeah, but you can visualize in your mind, right? So basically, this is how much I'm willing to offer of good 1 and good 2 given the price. This is what my offer here. Now, consumer 2, because preferences are the same, is structurally similar, but look at the income. Income now is endogenous, as is equal to 2P1 plus P2. Got it? So now, how do I find a price, if any, that creates mutual beneficial trade, or therefore a valuation equilibrium in this Edgeworth box? So first of all, right, I know that to determine valuation equilibrium prices, note that these prices, the total amount of good 1 consumed by the 2 consumers must equal to 3. Okay, so this is a feasibility constraint. So now if I adapt offer curve of individual 1 of good 1 must offer plus offer curve of individual 2 of good 1, this has to be equal to 3. Remember, our feasibility equation was less than equal, but I know that Cobb-Douglas are monotone and have this property that basically make you consume at the budget line, right? So that means that I will never be with inequality, right? Because else there will always be some locally non-associated allocation that I will push and go up. So it has to be with equality. So if I solve this equation with respect to prices, then I get the following relative price. So P1 star over P2 is equal to alpha 1 minus alpha. So this is, yeah.
We can also do this with good 2 as well, right? 1
Yeah,
minus
so
alpha.
it doesn't matter which good you pick, it will give you the same relative price. So this is a property of these models. So because of homogeneity of degree 0, you can always forget about one market and just solve the other, right? And so this was in the previous lecture note as well. And so in this particular case, and this is very special for Cobb-Douglas, same Cobb-Douglas utilities, you get not only existence of a well-rationed price equilibrium, but also you get uniqueness, okay? And now look at the price. So what is the exchange rate in this economy? Well, alpha is this parameter that tells you the fraction of income you will spend on good 1, right? And 1 minus alpha is the fraction of income you will spend on good 2. So what is the relative exchange rate between apples and oranges? Well, alpha divided by 1 minus alpha, right? So plugging numbers. So imagine that these guys like the same apples and oranges, right? So alpha is equal to 1/2. So what are relative prices? 1, right? Imagine they like more apples than oranges, right? So apples is 2/3, right? And there is 1/3, right? So, and then you can compute it, right? So exchange rate is going to change according to preferences, so the intensity of this preference. So it makes a lot of sense. So in this case, it's easy because both guys are Cobb-Douglas and then they have a unique equilibrium, okay? So let's go to the envision. So I want to show you a quick diagram of this. Can you see my screen? Yeah. Okay. So what's an Edgeworth box? So an Edgeworth box has basically agent 1 here. And here you have consumption of good 1, consumption of good 2, right? And here you have agent 2, right? So what is an endowment? So an endowment is some point basically on the Edgeworth box before the endowment. So how can you know what is the total endowment in the economy? Just looking at this figure. So basically you go here, and all this here is basically the total amount of omega 1, right? And all this quantity here is the total amount of good 2, okay? So the length of this rectangle is the total endowment, okay, of good 1 and good 2 according to the axis. Then the experimenter fixes some initial allocation, right? So this is called the endowment vector. So where is the endowment vector? Is wherever I want to put it. So for instance, imagine the experimenter wants to locate here the endowment vector, okay? So this is a point in this box. Now, so how much of this of good 2 agent 2 gets? This amount, right? And how much? So this is of course omega of good 2 for individual 2, okay? And then you do the same here, and this is omega of good 1 of individual 2, and then how much of this agent 1 gets this and this, okay? So you get here the corresponding omegas. So remember, endowment is just a point in the box. Now, preferences. So preferences are, of course, in this case, equivalent. So are the same preference in different curves for both agents. So agent 1 is the simplest to draw because this one is basically located in the usual orientation of our indifference curve map, right? So let me move it a little bit to get access to the colors. Yeah. So here you get the preferences of individual 1 increasing in this direction, right? And then with color blue, you get the preferences of individual 2 increasing in this direction, okay? Well, now, so in particular, right, whenever they basically become tangent to each other. So let me choose now a red color. Okay. So now, right, I'm gonna draw a price vector. So let me do this better. So this green line, which basically is a line that goes through the tangency point of these two preferences, right? And this is basically is the price vector. So this is the P star, and this here is the X star. Okay, so this is an equilibrium point. Okay. So what are the properties of this equilibrium point? Well, basically, they live in the tangency of the two indifference curves, right? Red and blue. And then the vector that goes through the tangency has to go through the endowment, okay? So 2 points, right? So 2 points in this two-dimensional figure determine a line, right? Completely. So the first point is the tangency of the indifference curves, and the second point is the endowment point. Okay, so this gives you the slope of the relative price.
So the price vector is all the combination of P1 and P2 that lies on that line, right? The tangent line.
So the slope of this red line is the price, right? So is the exchange rate between P1 and P2. So the slope here, right? This is P1 over P2 star, right? So this is a price. It's just a slope, okay? And then the allocation is this point that will tell you how much you consume, right? So this will tell you how much I consume for this individual, and this will tell me how much I consume for this other individual, okay? So let me draw it more clean in another figure, right? So you have here this thing. You have here an omega, right? And now you have the tangency point, right? And this is the equilibrium, right? Agent 1, agent 2. So basically, this is what's happening more schematically, right? So there is some tangency point, and then it goes through the endowment. The line is the price, the alpha divided by 1 minus alpha, and then basically you have this particular allocation, the excess depends on the initial endowment, right? So if you go back to the equations, what I'm describing is essentially the same mathematically, right? Is that you see that prices, they are just on a slope, right? But then allocations, they depend on the endowment level, right? So because they will determine the endogenous income, right? So when I say this line goes through the endowment, that only affects the allocations, right? Because that will tell you how rich you are, okay? So how do you get your own income, your own budget? Well, you get it by basically multiplying the endowment times the price. That's why the price line goes through the endowment, okay? So as you can see, so now let's go back to this. So look at, from the perspective of each of these agents, this line here is their own budget, okay? So from this direction to this direction, this is the budget of individual 1, right? And in this direction, this is the budget of individual 2, right? So as you can see, each of them is maximizing their own budget, right? Given the preferences. And then, of course, is a joint maximization process. This happens in this point. Both agents achieve their maximum utility subject to their endogenous budget. Okay? Got
Excuse
it?
me, Professor.
Yeah.
So the slope of that line going through the point X and the endowment, that is P1 star over P2 star, correct?
Yeah. The slope of that line is the relative price. Okay?
It is the minus P1 star divided by P2 star, right?
Sorry? Yeah, for
Minus.
sure. So we define a price as the relative price. This is just a schematic representation, right? So mathematically, I said relative price is P1 over P2. I understand that if you draw it in terms of coordinates, this slope is negative and prices are positive. That's fine. I'm just talking about the schematic representation, right? So, okay. Now, good. So again, this Edgeworth box, surprisingly, is very tricky to solve. So, and here I'm going to tell you this. So depends on what type of thinker you are. When I was in grad school, I'm not great at drawing and I'm not great at thinking in diagrams. So I learned to solve everything mathematically, and I did it. That's how I learned to solve these things. Now, other people use a lot the diagrams to solve these boxes. Now, so a lot of professors also are more schematic, or they like diagrams, so they will actually make problems that will be easier to solve drawing a picture. So in the end, you will have to draw a lot of these Edgeworth boxes and also combine it with solving it mathematically, and then find the best combination to solve this thing, okay? So when you have something as simple as the Cobb-Douglas, it's so trivial that you will be able to do it. But you will see in the problem sets coming that this is not as easy, right? And also when you practice for the core exam with previous year's exams, you will see that there are many tricky versions of this model, okay? Now, again, right now we're going to learn it in the most generality possible, which will allow you to cover any model, right? So the tricks of solving each of them is by practice, and I will send you a lot of problem sets with these Edgeworth boxes, many Edgeworth boxes, okay? Now, so let's go with the more formal general part. So Pareto optimality. So this is very important. Why do we care about these kind of models? And in the end, why are we studying these kind of systems? So these are very interesting systems because they basically tell you that you can put two agents following their own selfish interests, right? And then they can achieve basically an efficient outcome. An efficient outcome is basically described in the following way by using Pareto optimality. So we say an allocation X in the Edgeworth box is Pareto optimal or Pareto efficient if there is no other allocation X prime in this same Edgeworth box, such that X1 prime is greater than equal than Xi for all I, right? And actually I can define it with some heterogeneous preferences. And then it's actually better for some individual, okay? So that means that an allocation in an Edgeworth box is efficient or Pareto optimal. And you know, Pareto, I hope everyone knows why we name it like this, right? This is by Vilfredo Pareto, the Italian economist. So this is a notion of social optimality. So it says that something is optimal if there is no other allocation that is still feasible, that will be weakly preferred by every agent and strongly preferred by at least one agent. Okay, so this is a lot of words, but intuitively what you have to think is that this basically means that there is no waste in this economy, right? So imagine, for instance, an allocation where an individual is, doesn't want to trade. So he eats all the apples that he likes and he throws away the oranges, okay? So he cannot communicate with the other party, so he doesn't know the other guy likes oranges, right? So he throws away all oranges. So that's not Pareto optimal because the other guy likes oranges a bit, right? So he can be given all the oranges that the guy one doesn't like, okay? And therefore he will be happier strictly. And the other way we still get to eat all the apples that he likes so much. So therefore this allocation is not Pareto optimal because it's dominated by a second allocation in which the second agent eats all the oranges he wants, and the first agent gets to eat all the apples that he ate, okay? So that's an example of a Pareto suboptimal allocation, the one where he throws away all the oranges. So if you extend this idea, basically it means that if you have an economy where something that is desirable to other party is thrown away or wasted, that's a non-Pareto economy, right? So this is something that is wasteful. Someone could have used it, okay? So now, is this trivial? Not at all, right? Many economic systems actually are bad, and they don't let, they don't actually lead to Pareto efficient allocations, right? So for instance, remember that centralized systems were collapsing where a lot of the goods were being rotten, right? Because nobody were able to harvest them, right? And there is a surplus of some things that were overproduced and then underproduction of other things, okay? So this is wasteful. And then basically we're asking, we're looking at allocations that are not wasteful. So you cannot improve them in the Pareto sense. Now, Pareto allocations have nothing to do with equality or fairness, okay? So right now, I know that a lot of Western economies are trying to basically improve redistribution, okay? Pareto rankings are blind to redistribution. So you can have a Pareto allocation where if the first agent really likes apples and oranges and he's given by the experimenter all apples and oranges and he eats them all, that's a Pareto allocation, right? Because of his utility function that he likes both apple and oranges, he will eat it all, right? Then, the fact that the other guy doesn't eat anything, it doesn't matter to us because there is no other allocation in which the first agent is better off, okay? He will always be worse off. So for instance, Pareto allocations actually can be super unequal. So someone can eat everything and the other have nothing and is still Pareto optimal, okay? So Pareto allocation, as long as he eats it all, right? If he wasted something, he throws to the trash, then it's not Pareto, okay? So the only requirement is that this guy is a glutton, right? He can eat it all. So again, so remember, Pareto allocations are all about efficiency, but say nothing about equality, okay? So given that, I want you to understand the mathematical complexity of this, okay? So a Pareto allocation is basically a ranking over allocations of individuals of goods, right? So a ranking of a preference ranking ranks basically commodity bundles for an individual. But now we're talking about a social ranking. Do you understand? So if you're thinking from the point of view of a social planner, what is a desirable allocation? So now you have to compare not only bundles for each individual, but actually bundles of all the society consumption of goods, okay? So now, does it make sense to have a transitive and complete preferences over social profiles of consumption? Not really, right? So, but what is something that is reasonable still? And the Pareto allocation is basically a ranking over social allocations that is not complete, but is transitive, that still gives you some notion of what is best, okay? So think of the Pareto rank, right? So the Pareto rank is sometimes incomplete because two alternatives both are Pareto optimal, and you don't know which one is how to compare one to the other, right? But you can compare some inefficient allocations to some efficient allocations, so that's why it's incomplete. It's transitive, yeah. So this Pareto, basically this Pareto thing can also be understood as a binary preference relation on social outcomes. And now the question is this hard question, which is, imagine you're a social planner and you want to maximize the welfare of these two agents in my laboratory. So I want them to be the happiest possible, right? What should I do? So this next basically result that I'm going to give you is going to tell you that if you let them exchange freely, right, and they find such a price at which they can mutually beneficially trade, then they will achieve a Pareto allocation, okay, a Pareto optimum. So let's understand now in terms of geometry what is a Pareto set in the Edgeworth box. So in the Edgeworth box, a Pareto set is the set of allocations that are Pareto optimal for all possible endowments, okay? So the important thing here is to realize that when you're thinking about Pareto allocations, you have to think of all possible allocations when you move the endowment as an experimenter, right? So a Pareto set is actually, as you can see, all set of allocations that allow not waste, okay? So I'm going to tell you in a second what that means with examples, but basically I told you already. So when someone is throwing away to the trash things that are desirable to other party in the box, then that's of course wasteful and is not in the Pareto set. Now, the Pareto set has the property that any element has to be in the tangency of the preference curves. So remember, if you have an allocation that is at the tangency of the indifference curves, it means that is a point where the marginal rate of substitution between agent 1 and agent 2 of that good is the same as the marginal rate of substitution of the other agent, right? So basically they have the same slope. So anything that is away from that is going to mean that some of them can improve a bit their utilities by consuming some of the goods that are being wasted. So this is a geometric intuition. The definition is what matters, right? So you cannot find anyone that can improve their situation strongly while the rest remains the same. So any well-rational equilibrium allocation, and this is the important part, and this is basically a theorem that we're going to show later with more formality, is basically belongs to the Pareto set. So this means that if you let these agents in this box to trade, and they find a mutually beneficial trade situation, then their allocation will be in the Pareto set, which means the set of Pareto optimal allocation. So that means that letting the agents pursue their selfish interests, right, as long as they have a way to trade and as long as they find this price at which they can mutually and beneficially exchange, this will be a Pareto optimal allocation. Okay, and this is the famous invisible hand of Adam Smith, right? So remember this from your undergrad classes. So who remembers what was the invisible hand? Do you know who is Adam Smith, first of all? I don't know whether you're being taught these days. So who remembers the invisible hand? Rough intuition.
It's Adam Smith who thinks that the markets will, like the market forces will lead to the optimal, like when everyone's doing their, in their own self-interest, the market forces will lead to the equilibrium.
Okay, so two things, right? So Adam Smith really didn't talk about equilibrium. That was way later. But the important thing is this, right? So you said everyone pursuing their self-interest, right, will achieve a social optimum. Okay, So now let's qualify it. Social optimal equal to Pareto optimal, right? Selfish interest maximizing utility, right? So we say if everyone maximizes utility subject to their endogenous budget, given a price, equilibrating price, the equilibration price equilibrium, then a social optimum is achieved. Therefore, Pareto optimality is achieved. Okay, so now we have been more formal, right? Adam Smith was a great philosopher. He didn't formalize it. It's a great idea. So you can maximize a social system by letting the individual parts do a small part of the task, right? And then individually doing their own local computation, they can achieve a social optimum. Okay, that's amazing, right? So Adam Smith was way ahead of his time, right? So this is like, it's a really cool problem to think and to actually figure out that this can happen. But of course, he saw it on the wild. I mean, in his book, he says, it's not the butcher's self-interest, that brings, the meat, or the baker's self-interest that brings the bread to the market, right? Altruism, sorry, is their self-interest. They want to earn some money, they want to make some profit, and therefore because they're pursuing that selfish interest, they will actually create goods and services, right? So here Tyler copied. So it's not from the benevolence of the butcher, the brewer, or the baker. So I remember 2 out of 3. That we expect our dinner, but from the regard of their own self-interest, right? We address ourselves not to their humanity, but to their self-love, and never talk to them of our own necessities, but of their advantages. So, okay, so now I want to tell you something more modern, and I want you to think about it, right? So how does Uber works? Okay, so what is the market? So you have riders and you have the drivers, right? So Edgeworth Box situation, right? Now endowments, okay? So of course, agents, riders are endowed with some money, right? Imagine that's a good one. And then, of course, drivers are endowed with a car, right? That basically the service is moving in a subject from location X to Y, right? That's the other good. Okay, so you have this situation, and then what is the Pareto optimal allocation? So what is, first of all, the objective here? So riders want to get to a location, move to X to Y, right? And drivers wants to earn money, right? They want to maximize their profits given their effort and whatever. So okay, we're in the same setup. What is the social optimum here? So the social optimum, right, is that basically everyone maximizes their preferences, so they're able to reach their location with the smallest amount of issues and cost, and the drivers, of course, maximize their profit, right? So given their costs, they maximize whatever they earn. Okay, amazing. So now, how does trade happen? So who remembers how trade happened in the wild before Uber, right? So how do drivers and riders come up with an exchange rate? So who can tell me your own experience, right? We're from different countries as well, so it changes a lot. But before Uber, how did it work? So how was a fare, a cab fare fixed?
It's by the meter, right? So how much comes with the meter? It was usually the drivers who are offering the menu of choices, right? Prices, right? And we as the riders used to pick, okay, we are.
You have a taximeter, right? Someone came up with that, and then, but you basically it's miles, and then you fix a rate, right? Who fixes that rate?
The government.
Sometimes, but sometimes also the own company, right? So you have a co-op, right? It's a collection of cabs that they belong to some place, and they fix a ride. Sometimes it's the local government, right? But sometimes there is competition. So some of them are cheaper, other are deluxe, right? Some of them were safer, whatever. Okay, but somehow, by a lot of institutional process, negotiation, government, and so on, and even before the government, right? At least in Ecuador, you can actually negotiate with them, right? You say, how much is from getting to this place to this other place? $10. Well, that's too much. Well, 5. Okay. Yeah, so you can bargain. And so this is not a theory of price formation. So price formation is super complex, and sometimes we don't care because it's just too idiosyncratic. But we are thinking of a system where there is a signal, right? Which is this famous exchange rate given the taximeter, right? So you say, how much, kilometers is this amount, okay? And then, given this, people can actually meet. Now, how they meet in the market? Well, previously, homegrown markets, right? You have random matching. So you were walking in the street and you were looking for a taxi cab, you did a signal, right? Someone stopped by. So random matching, right? But now how does it work? With Uber, now the matching is through a GPS, right? And then someone moved into an area and then, they have a matching algorithm. Okay, so now you have a kind of an artificially done market, right? But what is the important thing? This is not a model about matching as well, okay? So we abstract from that. So what is this model about? This model is all about the price signal, right? So we forget about how people are matched in the market. We already assume they meet somehow. We forget about how the price is formed, how the exchange price is formed, or they are informed about the price, right? We're assuming that they already know the price. They are given by someone the price. We're not forcing them to trade. We're just telling them the price and they understand it, okay? So once you have done that, then what happens? Then each agent, given the price, computes their endowment, right? They know how rich they are. And then they decide to trade or not. And then they maximize their preferences, right? Which means basically equating their marginal rate of substitution to the relative price, okay? So now this is pretty cool because imagine what happened in the old markets of taxi cabs and in the new market, right? So originally, what will be the problem of the planifier? Is, I have to move all these people that are going from different places to other different locations. How can I do it in the most optimal way? So imagine you are a centralized guy in the 60s, right? So what do? It's a super hard problem, right? You have to find where these guys are, then how to move them. Then what do? You create a line like the airport, right? Which is a mess, right? You have to do a huge line and then you wait for a cab and then you're sending to different locations. So this is a super complex problem, how to move all these people from one location to another. So instead of solving that super hard problem that maybe doesn't have a centralized solution, then you just create a coordination device, which is a price, is a number, right? This is a number that you will pay to move from this location to this other location. Do you accept this price or not? Do you take the cab? Do you take the ride? Yes or no? Right? So now doing that basically simplifies this hard social problem to a problem of local maximization, okay? Because the price creates a local signal that allows you to locally maximize your own utility, okay? And then we're back to Adam Smith, okay? So Adam Smith figured out that complex coordination can happen by means of prices. So prices are this number that allows everyone to behave in their best interest in a way that allows social coordination. Now, important caveat, right? Again, this is not a model trying to describe how real life exchange happens, right? Because we know that in order for markets to exist, there has to be, matching. There has to be some way to fix prices. Markets live with regulation. Markets have a lot of imperfection. Real markets have a lot of imperfections, regulations, and so on. So this is not a model at this stage that is trying to model how real prices are formed. Not at all. This is just a description of how you can have a local or individual optimization reaching a social optimum, okay? That's the only objective here, okay? Now, now let's understand mathematically what's going on here. So we're going to define this general setup, which is an equilibrium with transfers, and then we're going to move to a different kind of economy. So any question here before we move forward?
So Victor, when we're talking about Uber, so there is no wastage in Uber. So like if a rider doesn't have a ride, so you're talking about like Pareto optimal allocations, right? So when you talk about Uber rides, so probably it's not Pareto optimal, that Uber market, probably not. Right?
So So Pareto optimality is an ideal, right? So, but remember the idea of Uber. So here, what you have is an adaptive price system, right? So basically, if there is a rider that cannot get a cab, a taxi, then what do? They adjust prices to increase it, right? Such that more riders are attracted to the area, right? And then what happens, for instance, if a rider wants to supply the ride, but nobody wants to take the cab, then you lower the fare such that someone is willing to do it, right? And that solves part of the problem, right? Because by moving the prices around, then you equate excess demand with, of course, supply, okay? So remember, as you increase prices, people are more willing to offer their services, okay? But also demand lowers. So you are basically finding a middle point. And that's why this surge price happens, right? So again, price formation is complex. And this is a subject of engineering, right? Pricing. We're assuming this somehow happened already. And there is one price in the middle that equates supply and demand, okay? That's what's going on. Now, again, this is not a theory of how prices are formed. I have said this many times before. So I'm not describing the price search algorithm in Uber. I'm just saying at some point in this price search algorithm, a transaction happens. Someone takes a ride, okay? And that's a situation that is very close to the social optimum. What I'm saying is that Uber is trying to minimize the lazy cabs and the riders that are not using their platform, right? So they have the same objective as Pareto optimality, no waste. So are you going to be at the perfect Pareto location? Not really, but you can approximate it. The key thing I'm telling you is how Uber achieves their objective, right? And it's not by using a computer, sending a cab to some location, owning the car, right? And then letting them take the rider to other place. What they're doing instead is letting each individual, worker for Uber to decide whether or not they take the rider. So they're using the human intelligence, right? Now, think about the problem if they replace it by self-driven cars that are owned by Uber. So now you actually have to do the centralized problem, right? So it's not only the problem that cars drive themselves, but also cars have to decide now whether a fare is good enough for them, right? So again, what I'm telling you is that Uber is not only profiting from the actual service of driving the car, but actually from the human processing of the marginal rate of substitution of these different cab riders, deciding, given the traffic, their experience, and so on, whether or not they should go to a certain location and bring this person from X to Y, right? They are deciding whether this price is good enough for them. So they are using information in the brains of the riders, of the cab owners, right? That basically makes them richer, right? So that's the incredible part.
So how efficient Uber is depends on how efficiently they adjust the prices, right? Like how quickly they can adjust the prices, right?
Yeah. So the key is this, right? So what I'm telling you is that what is our assumption here is that each agent is maximizing. Okay. So the solution to this problem depends on how good each individual part is at maximizing, right? You see? So why it works so well in Uber? Well, it doesn't work. Maybe it doesn't work so well, but that's why maybe they're struggling still with profits, right? But the key is that you depend, of course, on how good these individual agents are to maximize. Okay, so if each of them is maximizing, the theorem tells you that then the location is Pareto optimal. Okay. Now let me tell you something. We're studying in attention, right? So I'm just going to do this footnote, then keep going. So, but imagine you have inattentive agents, right? And now you have the price search, right? So is it going to work, for instance, if someone is not looking at their Uber app and checking each time the price is changing? So does the price search works? Not at all, because one of them is not looking at the price change, right? So yeah, so you have to basically fight against inattention, right? And that's why you're getting these reminders of all apps telling you, by the way, price has changed, right? Remember us, right? So inattention is the big obstacle to local optimization of these systems, okay? because you need full information in the sense of knowing the price and understanding the price to optimize. Okay, but what I want you to understand is that this theory is basically a theory where once you have seen the price, you can coordinate through the price. Okay. Now, so let's go, and we have an hour, so I want to cover the next model. So an allocation X star in the Edgeworth box is basically an equilibrium with transfers if there is a price system P star and well transferred T1, T2, such that T1 plus T2 are equal to 0. So basically, this means that in particular, you can go to this Edgeworth box, take away a tax over the endowment, and then redistribute it in any way I want. And I'm going to define the new maximization given the new endowments by means of this lump sum tax as a price equilibrium with transfers. Okay. So basically, this definition is going to become useful in a second, but what I want you to tell you is that, and this is claim 9, if the preferences of the consumer in the Edgeworth box are continuous, convex, strongly monotone, so remember we have added way more assumptions here, then any Pareto optimal allocation is supportable as an equilibrium with transfer. So what does this say is that imagine now I now have some preferences over the different Pareto allocations, right? Because you're Uber, and now, for instance, you care about getting out people of certain area, right? Because, for instance, there was some sort of security incident, and you want everyone in this red zone to get out, okay, as fast as possible. So how do you do it? So can you change the economy or the box such that you still optimize, so Pareto optimality, but achieve a different allocation than the initial one, okay? So what do you need to do? So remember here, what are the endowments? So is the number, the car, right? So where you are located somehow. This is for the supply side. So what do you need to do? So, well, you need to basically move a lot of the endowment to the red area, right? So you have changed the endowment of the economy. Now you let them optimize, and then this is going to change the price source to a new price, which is lower for that area, and move it away. Now, a more modern, more traditional example is the following. Imagine you care about equality. So you can have two equilibriums that are Pareto. So you can have two allocations that are Pareto. So equilibrium doesn't have anything to do with Pareto. So I misuse the name. So a Pareto allocation, the one where is, you know, this monster Pareto optimality, where one guy eats all apples and oranges, right? And he was endowed with all 10 apples and 10 oranges, and he ate it all. That's Pareto allocation 1. And then Pareto allocation 2 is both of them get to eat the same thing. 5 apples, 5 oranges, 5 apples, 5 oranges. So both of them are Pareto optimal, right? Now you are the designer and you want to implement the equalitarian outcome. How can you do it without messing up with the local optimization? How do you do it? Well, the solution is to tax the endowment. So I take the initial endowments away, right? And now I give the endowments to them in an equal way, okay? Once I have given the new endowments in the Edgeworth box, so each of them gets same amounts of apple and oranges, I let them exchange, okay? And then they come up with a new solution. This is a price equilibrium with transfer. What I'm saying here is that I can take basically any allocation that is Pareto optimal and then find a particular tax scheme that is lump sum, so no waste, such that I achieve the Pareto allocation. So I can implement whatever I want from the Pareto frontier. Do you understand? So this is basically, this is a good compromise when, given that Pareto allocation doesn't say anything about equality, maybe you can put an additional criterion to refine the solutions over the Pareto frontier, right? And this is telling me a practical way to do it without having to centralize. So instead of centralizing the solution, I just can redistribute endowments. Now, this is not telling me how to do it in practice, right? This is just telling me it is possible that I find a tax scheme such that I can achieve any Pareto allocation that I want. Do you understand? So these are two problems that is called. The first one is the problem of the invisible hand, that we're gonna call it from now on the first welfare theorem. And this basically tells me that if you are a well-rationed equilibrium, you're going to be in the Pareto frontier, or you're going to be a Pareto optimal allocation. So this is the invisible hand, or first welfare theorem.
So
we're going to study with Kerr in a second. Yep.
Walrasian equilibrium implies Pareto optimal allocations, but not the other way around, right?
Not the other way around, but you can do this result here, which is a partial converse, which tells you that if preferences are continuous, convex, and strongly monotone, you can take any point in the Pareto frontier, right? And then support it as a price equilibrium with transfers, okay? So basically, you can create an economy where you can redistribute endowments in a way that they are going to reach the exact Pareto allocation that you desire to implement, okay?
Now, is there a set that's like smaller than the set of Pareto optimal allocations, but also larger than the well-rationed equilibrium?
Yeah, for sure. For instance, one such set that we're going to study later is called the core economy. So this is basically the set of allocations that no pair or no coalition of individuals inside this box. So imagine you have more than two, possibly have three agents. So then what are the coalitions of agents? So it's basically agent 1 and 2 can get away, agent 2 and 3, agent 1, 2, 3, agent 1, agent 2, agent 3, right? Alone. So all of the subsets of individuals in this box can decide, for instance, to take their endowments, go out of the experimental room and say, we don't want to trade with this other guy, and we don't want this price. Let's do our own economy, right? And then get our own exchange rate and then maximize. So all the allocations that cannot be blocked by these dissidents, right? Then this is called the core economy. So any well-rationed allocation is going to be in the core. I'm going to repeat this again at some point, but at this stage you asked. And then basically the Pareto allocations are going to be intersected with this core, right? Because the Pareto allocations are the ones that are not blocked by the large coalition of all agents, okay? So in the economies with two goods, then the core is going to be larger than the well-rationed equilibrium, right? Smaller than the Pareto set for two goods. For three goods can be, actually, there is no discontainment thing. Okay, so let's go to the consumer and producer economy. So instead of now having two agents that don't have production, so just free disposal, and have a means to exchange, now let's study this typical kind of macro-ish model where there is one consumer and one producer, okay? So this is another example of a general equilibrium model, and this shows up a lot in macro. So we're going to study and understand within our notation. So in this economy, there is a consumer and a technology. The consumer has continuous, convex, strongly monotone preferences defined over two goods, leisure X1 and consumption of coconuts, right? Good two. So this is the typical Robinson-Crusoe economy, right? So leisure and coconuts or consumption good X2. The endowment is basically, what is endowment here? So given that we have time as being leisure, basically the units of consumption of leisure is time, then endowment is 24 hours, which is overline L. And there is no consumption good here. So the aggregate endowment of the consumption good is 0. However, because there is a technology, you can transform hours of work into consumption good. Okay, so you can climb the tree and take coconuts to the floor, right? So the consumer can produce the consumption goods by means of labor, okay? That's why it's the coconut, because there is no other input, so just grab it from the tree. And so this production function is a very simple function of one input, where this is the labor you put into taking the coconut out of the tree. And this is denoted by a small f offset. To produce the output, the firm must hire the consumer. So all of this wording is from macro, right? But what it means is that the firm uses the labor of the consumer. effectively purchasing some of the consumer's leisure from him. So here, what are prices? The prices are exchange rate. So basically, what are the goods? So the goods are here time or leisure, and then the other is coconuts. So the relative rate of exchange between these two goods is going to determine the prices of the output and of course the wages. So you can normalize the wages to W here. So we're going to see that in a second. But right now I'm going to use the full notation without normalizing, so you understand what's going on. But remember, we can always normalize one of the price to one. So we assume that firms are profit maximizing. So given their prices, that's the only information they use to maximize profits. And then let P be the price of the output and W be the price of labor. And then, of course, the relative price is the exchange rate. So what does the firm do? Well, they maximize profits. So they maximize sales, which is price of the output times coconuts, minus the labor, which is wage times the labor invested there. So given the PW, the prices, the firm's optimal labor demand is set of PW. So this is how much the firm takes as an input, the labor of the worker. And this depends on the price of the output and on the price of the input. And the output is Q of PW. So remember, this optimal demand is already the non-conditional on the quantity, is already the final input demand. So this is the optimal supply level. So the solution to this problem is how much output do I produce and how much labor do I consume as a firm. And then the profits of the firm are pi of P and W. Now, remember, the key to the general equilibrium models is that income is endogenous. So what is the income of the consumer? So the consumer owns completely the firm. So the first source of income is the total profit of the firm. And the second source of income is the labor. So how much labor do I sell to the firm? So that's total hours that I work, which is overline L, the endowment of time, minus the leisure consumption, which is the amount of hours I have worked, times the W. So this gives me endogenous income. Everyone understands this part here? So income here is the sum of profits plus wages, multiplied by labor. Okay? And then there's only one consumption good, coconuts, and I multiply it by its own price. I maximize this problem, and now I'm going to get as a solution the consumption of leisure, x1, as a function of price of the output and as a function of wages, and then consumption of coconuts. Okay? And now, what is a Walrasian equilibrium here? So remember that you have to have a market clearing condition, which means that all consumption is equal to all supply plus endowments. But because coconuts have endowment equal to 0, then this equation is the complete market clearing condition for the market of coconuts. So X2 is the consumption of coconuts of the consumer, and Q is the production of coconuts. So now I'm asking, is there any P star and W star that clears the market, right? If that happens, then because of homogeneity of degree 0, immediately the next market is going to be clear. And what is the market of the labor? So whatever the firm uses as labor or employs as labor is equal to the supply of labor by the agent, right? So this is the market of labor, and this is labor supply on the right-hand side and labor demand on the left-hand side. And this is basically demand of coconuts in the left-hand side and supply of coconuts in the right-hand side, okay? So claim, a particular consumption-leisure combination can arise in a competitive equilibrium, even only if it maximizes the consumer's utility, subject to the economist's technological endowment constraints, which is to say that the allocation here is also Pareto optimal, okay? And more than that, this solves, basically this solves the centralized problem. So again, this is all about decentralized solution to potentially hard problems to solve at the social level. So imagine now you have a social planifier that wants to make as happy as possible to Robinson Crusoe. what will this guy do, the central planifier? So he will basically maximize the utility of Robinson Crusoe subject to the technological constraint, right? So then what's going on here? So the optimization problem of the central planner is basically maximizing. So let me write this thing here. So you can imagine a central planner that maximizes the consumption of good 2 and good 1, right? So this is the total utility. Let me make it a little bit larger. The utility of Robinson Crusoe, which is of course a function of x1, x2. And then subject to what? To the fact that x2 is equal to f of labor minus x1. Okay, so this is the central planner problem. Do you agree? Now, the solution to the central planner problem is basically a Pareto optimum, right? There is no way you can improve the situation here. So what claim 10 is saying is that the decentralized problem stated before has the same solution as the central planner problem. Okay? And what is different here? Well, if you go back to this problem, now the only information that the firm has is the price of output and the wage, okay? And they know their own technology, but they don't need to know the preferences of the consumer, okay? So it's all about information. They only receive a number, price of output and labor price, okay? They don't know the preferences of the consumer. And they maximize their own profits, okay? They only know their technology. And then from the consumer side, they don't have the technology of the firm, right? They only receive a check with the profit and the pay stuff, okay? So the dividends and the pay stuff. So, and then knowing the prices of labor and output, the coconuts, you maximize your own preferences without knowing the technology, okay? So even if this problem seems mathematically very close, because they are, in terms of information content, they are very different, right? The central planner has to know a lot, right? They actually need to know the preferences and technology. So they have to need both sides, right? While this decentralized problem only needs to know preferences in the first problem, and in the second problem, you only need to know your technology. So prices allows us to break the problem into two separate problems that use less information, okay? So imagine you basically are trying to do this in a computer, right? So basically you can try to think of just in pure algorithmic terms. So you want to solve this problem, and imagine this is not an easy problem. Imagine there are hundreds of goods, okay? So now this is a very complex nonlinear problem with nonlinear but convex budget constraints. How can you simplify it? Well, this theorem is telling me that I can break it into two problems, right? Each of them, the first one basically is a problem without constraints, and the second problem is a problem with linear constraints, right? So basically, I can break the big problem of the central planner into two problems, right? Now, imagine that I not only have two agents, but I have 100 consumers and 100 firms. Then the centralized problem is even larger, right? Even memory-wise, it gets super complex. Now, this result is telling me I can break it into 100 problems for the consumer and 100 problems for the firm, right? So I can parallelize it, right? I can set each computation to a GPU node, GPU graphical processing unit, so a parallel computer. Do you get it? So basically, in modern terms, what Adam Smith was saying is markets are kind of parallel computation of a social problem. Do you get it? So basically, you can break a big problem into smaller pieces and then give each piece to a processor, which is a human, a trader, right? A firm. And then let them maximize their part and then When you put together the pieces, everything works. But what is the glue of this problem? The prices. Okay, prices is the common array that you're given to each GPU node. So this is the information everyone gets. Okay, so W and P are common knowledge. They all know it, right? And they all accept it. They all take it as given. Do you understand? Okay, so basically the modern way to think about this, and you know, we have different language. So in the time of Mascolel and in the time this was invented, like post-war, all the people invested a lot of time on this because this has a strong ideological content, right? Because they say, look, that's why USSR is lame and USS is and the USA is great, right? Because USSR is kind of the central planner. They had Leontiev, you know, but Leontiev didn't have good computers, so he messed it up, right? But now, you know, things have changed. So now, you know, we don't have Leontiev, but we have the Uber guys, which had a lot of GPU computing. And now things are different, right? But they learn that you can have kind of mixed models where you can have this mixed centralized problem with the centralized solutions, right? So what I'm going to tell you is basically that most markets in the present real markets are mixes, right? So you get this kind of partial central command, partial decentralized system. But the key idea of Adam Smith, you know, is this decentralization of complex social optima by means of parallelization. So you break it, right? Divide and conquer. So you can break it into smaller pieces, and each agent will maximize their own local utility subject to a price. And these prices are all the information these guys need, okay? So prices contain all information needed about a very complex economy. So in particular, a central planifier will need to know all of your preferences, right? So Uber will need to know every one's of you preferences for rides, locations, patients, and so on, right? They can estimate some of that information using models of stochastic choice, discrete choice, right? But they're not going to do a perfect job, right? And the same thing for riders, right? How do I estimate the technology of a cab rider? So what is a technology? So is, you know, you have your different car, different gas efficiency, how good you are as a driver, how good the roads are in London versus San Francisco, right? So all of this is local information that Uber doesn't know completely. So what do? So instead of trying to learn this completely and do a centralized problem as a la Leontiev, right? They actually create an approximate problem, right? Try to solve, use it to come up with a search price, which is pretty much a bad solution, initial solution. So the initialization of the system. You give this price to all of the local agents, let them use their local information, their actual preferences, their actual technology, and then come up with a trade. If there is no trade, I adjust again my system, which is what I learned, right, from the feedback. Again, central command, and then I propose a new price, right? And now go again, do your local maximization and so on. If there is a trade, I'm done, right? So now Uber profits, you see? So that's in real life what happens. So in real life, we have this mix of central command and decentralized solutions. So in real life, these two things are actually very mixed. So but I'm telling you this because right now, economists, we have changed a lot what we do, right? So in the 60s, all this chapter was almost ideological. So it's very mathematical and nice, but basically it was like a fairy tale. So at this point of the class, I will tell you, and that's why the centralized system are better than centralized system, the end. Remember, right? That will be the end. Now I'm telling you, look, no. There is no market such as the ones in our textbooks. So we're not trying to describe markets. It's not a theory of markets, so forget it. We are learning that many hard social centralized problems can be decentralized, right? And decentralizing is better because decentralizers can use local information, is more robust, you can parallelize it, all sort of benefits, right? So basically it means that a good way to solve complex social central command problem is to decentralize it, right? And can you use it? Yes. And actually the important thing is sometimes the markets that are going to look more like the textbook are the markets we create, right? So basically at some point, if one of you decide to create your own app you know that you can actually use this power of decentralized optimization to solve your hard problem, right? So basically, this is how we think about it. It's more prices by design. So we want to design markets, and this is market design eventually that we're gonna get there. And basically, you are not studying real markets at this stage, but we're thinking of this object called market that basically allows you to solve a social problem, making it into an individual problem. Okay, so this is the takeaway I want you to learn from this. And this is the insight from Edgeworth, which basically was we can break these complex problems into smaller pieces. So there you have it. Economist Schumann. Yeah, I couldn't hear you.
Yeah. So do you want to decentralize as small as possible, or like, so when you're telling of breaking down the central into smaller decentralized, right? So
Yeah. So
the
again,
smallest possible, or like how do you?
But this question is a question about design, or is a question about what happens in real life, right? So if it is about design, then I will tell you it depends on the situation. So for instance, if I'm trying to program something in parallel, right? So it depends on how many parallel processors I have. So if I have, 10,000 processors, then I want to basically make my program as small as possible, such to use the 10,000 ones, and all of them are super fast, right? If I only have 10, then all of them have to actually solve more complex problems. And this is similar to an economy. Versus if you have a conglomerate of firms, right? That, for instance, you have here these financial groups that own a lot of firms together. So they will maximize the profit of maybe 100 firms, right? So this is kind of a big processor, right? They have a lot of capabilities to maximize and so on. Consumers usually decentralized, but inside a household, sometimes you can have some person maximizing the consumption of food for all the 5 guys there, right? Inside the household. So, I mean, that's kind of what happens in real life. But what I'm telling you here is more that hard problems that are centralized can be basically break into pieces. And this is basically what I mean by the second welfare theorem, right? And the first welfare theorem is telling me that I can actually reach the social optimal by locally maximizing, okay? And then the second welfare theorem is telling me I can actually move in the frontier of optimal values by changing the endowments, okay? So let me just move away around endowments. I can achieve any point there as long as your preferences are convex, okay? And then we're gonna go back to this. So these are deep concepts that we're gonna get again. And we're gonna stop there. So yeah, let me stop the recording. So right now you're